Welcome back to Blueprint to Reality. Today, we're diving into a game changer in the construction industry, prefabrication. In a world where efficiency and sustainability are crucial, prefabrication is helping builders complete projects faster, with less waste, and often at a lower cost. But what exactly is prefabrication, and how is it revolutionizing construction as we know it? Let's explore. What is prefabrication? Prefabrication, or prefab for short, involves constructing building elements, like walls, floors, and even entire rooms, in a controlled factory environment before they're transported to the construction site. Think of it as creating the pieces of a puzzle in advance, then assembling them on location. This approach is very different from traditional construction, where each piece is built directly on site. By assembling components in a factory setting, builders can control quality, reduce weather-related delays, and create multiple pieces simultaneously. Faster construction, lower costs. One of the biggest advantages of prefabrication is speed. Because elements are built in factories ahead of time, on-site assembly is much faster. What used to take months to build can now be completed in weeks, which is especially valuable for projects in crowded cities where space and time are limited. Faster builds also mean fewer labor costs and less need for on-site equipment, making prefabrication a more affordable option overall. In the world of construction, where time is money, prefab is a revolutionary way to deliver projects on time and on budget, reducing waste and increasing sustainability. Construction sites are known for generating waste, and used materials, packaging, and debris often end up in landfills. Prefabrication minimizes this waste by using precision manufacturing to create exactly the right amount of material for each component. Because factories can recycle and use materials more efficiently than traditional construction sites, prefab reduces environmental impact. Additionally, building components in controlled environments reduces the carbon footprint by cutting down on heavy machinery and equipment usage at construction sites. Prefabrication is proving to be a sustainable solution that aligns with today's focus on eco-friendly building practices. Versatility and innovation. Prefab isn't just for homes and small buildings. Today, it's being used for everything from hospitals and schools to skyscrapers. Modular construction, a type of prefabrication, allows entire sections of a building to be stacked and arranged in various layouts, giving architects and engineers greater flexibility. Prefab has also led to innovations like 3D printing, where parts of buildings are printed directly in factories. This versatility allows for creative, customizable designs while maintaining the efficiency benefits of prefab. The possibilities for prefabrication in construction are only growing as technology advances. A new era in construction. Prefabrication is transforming the construction industry, delivering faster builds, lower costs, reduced waste, and incredible flexibility. By moving much of the building process off-site, prefabrication offers a sustainable, efficient alternative to traditional methods. As the demand for rapid, eco-friendly construction continues to grow, prefab is set to play a central role in building our future cities. Thanks for joining us on Blueprint to Reality. If you're excited about how new technologies are changing the world of construction, make sure to subscribe and stay tuned. See you next time as we explore more innovations shaping the future of building. Welcome back to Blueprint to Reality. Today, we're diving into a fundamental concept in structural engineering: load distribution. Whether it's a towering skyscraper, a graceful bridge, or a compact house, understanding how to distribute loads is essential for keeping structures strong, stable, and safe. So, what exactly is load distribution, and how do engineers use it to create resilient buildings? Let's explore. What is load distribution? In the simplest terms, load distribution is the way forces and weights, like gravity, wind, and the weight of materials, are spread throughout a structure. Every building or bridge experiences loads that push, pull, or press down on it, and these loads must be managed effectively. Engineers strategically design each element of a structure, from columns to beams to foundations, to bear a specific part of the total load, preventing any single part from being overstressed. Without proper load distribution, structures could bend, crack, or even collapse. Types of loads. Engineers work with several types of loads that impact a structure in different ways. Dead loads are the permanent weight of the structure itself, like the weight of walls, floors, and beams. Live loads include temporary forces, such as people, furniture, and vehicles, which change over time. Then there are environmental loads, like wind, snow, and seismic forces, which add extra challenges. By considering each of these load types, engineers design structures to withstand daily use and unexpected forces, ensuring they remain safe under various conditions. Key load-bearing elements. Structures rely on specific elements to distribute loads. Beams, columns, and foundations are the main load-bearing elements. Beams spread horizontal loads across columns, which transfer them downward. Columns act like the legs of the structure, channeling forces toward the foundation, which then spreads the load into the ground. Imagine a tall building. Its columns and beams are carefully calculated to handle the building's weight and any additional loads it faces, allowing it to stand tall without excess strain on any one part. This interconnected network is what keeps buildings standing strong. Load paths and redundancy. An important concept in load distribution is the load path, the route that loads take through a structure down to the ground. Engineers design clear load paths to ensure that loads are evenly transferred and spread out. Redundancy is also critical. If one load path fails, there are backup paths that can handle the extra weight, preventing catastrophic collapse. For example, bridges often have multiple cables or trusses that work together, so if one weakens, the others can still support the load. This built-in redundancy is a core principle of safe structural design, building with safety and stability. The science of load distribution is vital to creating buildings, bridges, and other structures that are safe and reliable. By understanding the different types of loads, using strong load-bearing elements, and creating secure load paths, engineers design structures that stand up to daily use and unexpected forces alike. This invisible science ensures that the structures around us remain solid, even when we can't see the forces at play. Thank you for tuning into Blueprint to Reality. If you're fascinated by the principles that keep our world standing, make sure to subscribe. Join us next time as we explore more engineering marvels and the science behind them. See you soon. Welcome back to Blueprint to Reality. Today, we're tackling a critical question. How do engineers ensure safety in large structures? From towering skyscrapers to massive bridges and sprawling stadiums, these feats of engineering are more than just impressive. They're carefully designed to keep people safe. So, what goes on behind the scenes to make sure that large structures stand strong and secure? The role of structural analysis. The first step in ensuring safety is understanding the forces that act on a structure. Engineers perform detailed structural analysis, which is essentially predicting how a building or bridge will react to various stresses, like the weight of materials, people, wind, and even potential earthquakes. By simulating these forces, engineers identify weak points and reinforce them. Every large structure you see has gone through this process, where every detail is examined to make sure it can handle the loads it'll face daily and over time. Structural analysis forms the backbone of a safe design, letting engineers catch and fix problems long before they become risks. Choosing the right materials. The materials chosen for structure are crucial for its strength and durability. Engineers carefully select materials that are both strong and flexible enough to withstand natural forces. For example, steel and concrete are common in skyscrapers because they can handle immense loads and resist wind and earthquakes. For bridges, engineers might use specially treated steel that can withstand corrosion from weather and saltwater. By understanding each material's properties and limitations, engineers ensure that every component is up to the task, creating structures that are both safe and durable in various conditions. Safety features and redundancy. One of the most fascinating aspects of structural safety is redundancy. Engineers design multiple layers of protection so that if one part of the structure fails, others will step in to hold it up. For example, in bridges, tension cables or trusses might be added as backup support. Skyscrapers often have multiple core systems, meaning if one part weakens, the others maintain stability. Earthquake-resistant buildings even have shock-absorbing bases to reduce ground shaking effects. These safety features act as fail-safes, protecting against unforeseen challenges and keeping structures resilient. Real-world testing and monitoring. Once a structure is built, the safety checks don't end. Engineers conduct tests like load testing, where weights are added to see if a structure holds up as expected. They might also install sensors in bridges and tall buildings to monitor for signs of stress or movement. These sensors collect real-time data, so if anything seems off, engineers can investigate and make repairs immediately. Monitoring technology is a key tool in extending the lifespan of structures and preventing disasters by catching issues before they grow serious. Creating large structures is an incredible accomplishment, but none of it would matter if they weren't safe. Engineers go to great lengths to ensure that every skyscraper, bridge, and stadium can handle the unexpected, from natural forces to daily wear and tear. Through careful analysis, material selection, built-in safety features, and constant monitoring, engineers transform massive structures into safe spaces for millions. Remember, behind every impressive building or bridge, there's a team of engineers working tirelessly to keep it safe. Thanks for watching Blueprint to Reality. If you're interested in learning more about the incredible world of engineering, don't forget to subscribe. Join us next time for more insights into how the world around us is built to last.